Okay, it's 10 o'clock. Welcome to day 3 of Organometallics. Alex, can you hear me okay in Florida? Wave your hands. Okay, good. And based on the feedback from the TAs, we decided to start today with a periodic table pop quiz. It will be graded. So, Joe, do you want to hand out?
Yeah, so it's just going to be blank pieces of paper.
No, just kidding. It's an April Fool's joke. Okay, but they put me up to it. But we have, in all seriousness, we've noticed, especially during some of the problems of the day, that people have a hard time remembering which group various transition metals are in. So we're going to, for the midterm, so you have plenty of time to prepare. For the midterm, there will be a midterm question where you need to draw recount the periodic table of transition metals, and it will be graded in part of your grade. If you don't remember it, then you can ask the TAs to fill it in for you, but then you'll lose some points for that. So this is just something you need to get familiar with, and I think it will really help, actually, your intuitive understanding of reactivity if you know where all of the transition metals are. We will not do the F1, but you can if you'd like in your free time. Okay, so that's one piece of administrative business. The other is, as a reminder, that Wikipedia articles are due now, the topic is due in a week and a half. Some people have already emailed me about the topic. You can do so at any time. If you are not sure and you want some advice, I'm happy to discuss that with you. And I think the TAs would also be happy to discuss that with you. But as a reminder, if you look in the syllabus, that's April 9th is the due date for picking a topic. And then the final piece of administrative business, maybe some of you have noticed, but we went ahead and posted all of the lecture videos to YouTube, and you can link them directly from the resources page on the website. These have actually been quite popular. They're getting like 100 downloads per day on average, probably not all from this class unless you're really enthusiastic. But this just makes things simpler, and particularly for people in the class who might be sitting in but not enrolled and don't have easy access to where the videos are posted. Hopefully this simplifies things. Okay, so today we're going to take a deep dive into metal ligand bonding properties. And as a quick recap, last week we learned about how to do essentially the accounting aspect of thinking about transition metal complexes, 18-electron rule, X-type ligand, L-type ligand, and how to make determinations like oxidation state, electron count, etc. So today we're going to focus more on the underlying theory of bonding, how to anticipate, based on molecular formula, what the connectivity of a given complex would be, what the geometry would be, and then how to think about its frontier orbitals. So today will be divided into a couple different parts. So first we'll talk generally about periodic trends. I call them basically trends in the transition metals series of the periodic table that are relevant to structure and reactivity. Then we'll talk about different theories that account for bonding and properties in transition metal complexes. And we'll build that up from sort of most simple to most complex. Hopefully this will establish a firm foundation for then moving into reactivity in the next lecture. So we'll talk, hopefully today will be another step towards building a firm foundation, and then we'll jump into elementary reactions on Wednesday. So first, to set the stage, let's talk a little bit about trends in the transition metal series of the periodic table. There's a handout that actually summarizes some of these, so don't feel the need to write them down. And I also took the liberty to not recapitulate some of these charts because I think that they summarize things much better than I could. Anyway, so one of the first points to make is that I would say that in general, most trends in the transition metal series are a little bit less continuous than they are in the main group. So certain rules that you learn to be true in main group elements. There are these same types of rules in the transition metal series, but there are more exceptions, and so you need to think more broadly when you're inferring properties from position on the periodic table. And then the other point that's important to make is that the properties of a complex and the individual metal element are not necessarily the same thing. They can be quite different depending on the coordination environment. Okay, so those are the two disclaimers, so to speak. So now let's talk about what we can say. And I think some of these points I said are summarized on the handout charts. So the first point is that there's an intimate interplay between d orbital energies and ionization potentials. I think this is somewhat intuitive. And there's a general trend of increasing ionization potential as you move left to right on the periodic table. So it is easier to remove electrons for more electropositive elements. I think this is easy to understand. And so, additionally, the energies of the orbitals of these more electronegative atoms are lower than the same orbitals for less electronegative atoms. So just to illustrate this point with an example, if we consider an arbitrary zirconium complex in the +2 oxidation state, and we think about its properties in comparison to an arbitrary palladium-2 complex, then we could say we would expect that the zirconium complex is going to be more easily oxidized, easier to take an electron away from that complex, more basic, more electron rich than its palladium +2 counterpart. And so this is generally true from left to right. What about from up to down? Well, things are a little bit more complex there. And so I guess I'll sort of leave it at that, that this tends to be more case-by-case specific. But one of the things that we can say is that as you go up and down a group, if you think about forming high oxidation state species, so high oxidation state we're defining by anything that's greater than or equal to +3, it's harder for a first row element compared to a third row element within a group. And so as an example, I'm sure many of you can shout out, although I won't ask you to do so, platinum-4 complexes that you've encountered during the course of your research, whereas corresponding nickel +4 complexes are much more rare. And there's been some nice work in the last 5 years or so from Melanie Sanford's group and others on these sorts of species. But when you make them and you find good ligands to stabilize them, then they're good publications in their own right. So this is still a challenge of getting high oxidation state in first row elements. So one other trend that has important consequences in terms of reactivity is size. And so here, one of the most pervasive effects is that as you go from the first row to the second row, the elements are quite a bit larger, and this is a direct consequence of the fact that you now are moving to a higher quantum number of the valence orbitals. And then, at first glance, somewhat counterintuitively, the third row elements are actually similar in terms of atomic size compared to second row. And so what's going on there? It's this effect called lanthanide contraction, which when you go from the second row to the third row, you introduce all of these lanthanide elements. And so that means that the nuclear charge of third row elements are significantly higher than second row. So there's a much bigger increase in nuclear charge as you go from here to here compared to here to here. And of course, nuclear charge has a direct consequence on atomic size. And then another general trend is that for complexes, at least of groups 4 through 7, that have the same charge and the same oxidation state, size increases. as you go from left to right. Sorry, size decreases from as you go left to right. Thanks. And again, this is just a reflection of the atomic charge as you go left to right. Okay, what about metal ligand bond strength? Again, these are general trends, but as you move down the periodic table, metal ligand bonds are stronger, and as you move up, they tend to be weaker. And one of the points to make here is that this is actually opposite to the trend that you see in the main group. So for example, in the main group, carbon-chlorine bond versus carbon-iodine bond, everyone will immediately recognize that carbon-iodine bond is significantly weaker. But the opposite would be expected in bonds to transition metals. So what is the origin of this? It's in part due to the fact that, remember, in general, metals are big, so when you get to when you move down the periodic table, you start to get better spatial overlap with ligand orbitals, and that the energy of ligand orbitals and metal orbitals tend to have better matching, particularly when you get to the third row. Okay, so that's just a quick primer on properties. Many of this information you can find directly in the Hartwig textbook if anybody wants to read more about that. So let's now transition into theories that can guide our thinking about metal-ligand interaction and bonding, and ultimately moving up to structure. And we'll start this with hard-soft acid-base theory. I think this is something that probably most people have heard mentioned at some point in their organic chemistry training. The basic idea is a simple one, which is that there's a spectrum of properties, hardness to softness. Hard elements tend to be small, densely charged, non-polarizable. So if you're thinking about counteranions, this would be fluoride, or alkoxides are hard anions. And then in contrast are soft ligands, or soft atoms, which are large, diffusely charged, and highly polarizable. And so these are typically, in terms of ligands, these are elements that are second-row elements or beyond, or those that are capable of multiple bonding. So basically, small, tightly packed charges, hard elements you can think of almost as like point charges, and soft are these large, diffuse, fluffy clouds. And so hard elements tend to interact with other hard elements better than maybe with soft elements, and vice versa. So essentially, this theory reduces to these two statements: that hard acids form more stable complexes with hard bases, soft acids form more stable complexes with soft bases. And there's on one of the handouts you can see quantitative examples that show this as you go from a proton as the hard acid to mercury, and as you go from fluoride all the way to iodide. And so the strongest interactions are between H and F and mercury and iodide. And that can be measured. And then there's also on a different handout, there's more details in terms of what elements are hard and soft as you move to different points in the periodic table. So in the interest of time, I won't belabor this point, but it's something to think about as you're trying to develop your intuition for complex properties, thinking about the character of the metal, the character of the ligand, and how strongly these are going to have an interaction in terms of hard-soft acid-base. Now, hard-soft acid-base theory really is just sort of a representation or a manifestation, rather, of what I've stated here. Is that as you if you consider a metal with diffuse orbitals and a ligand with diffuse orbitals, then these have better spatial overlap and thus form better bonding interactions. Okay, so now charging forward, but we'll save this. We'll come back to this chemist of the day. So charging forward now, we're moving to more refined pictures of structure. And so the first framework that you can think about bonding and structure in metal complexes is just through a simple VSEPR analysis of valence shell electron pair repulsion, which basically what VSEPR reduces to is that if you consider every bonding interaction as a lone pair of electrons, then these lone pairs of electrons will try to get to positions on a sphere that minimize their repulsion with one another, and there are a couple sorts of privileged geometries that they will have a tendency to adopt. And so here's how this breaks down for coordination number of 2 all the way up to 6. So with coordination number of 2, and don't necessarily feel the need to write this down. I think this table is actually reproduced verbatim in one of your handouts, just to save you some wrist muscle energy. So for coordination number 2, just like in main group element, well, to an extent like main group elements, it's sort of simple. There are two bonding situations. One is linear. You see this often with Volt-1 complexes. And the other is bent. So this is sort of analogous to the water, and you can see this in tin dichloride. For coordination number 3, there are 3 bonding situations, trigonal planar. So this would be like in the main group, you have 3 etherate, pyramidal, and T-shaped. Trigonal planar is somewhat common. Here are a few examples. Mercury triiodide, Gold-1 bonded to 3 counteranions, etc. Pyramidal and T-shaped, these are more specialized geometries. And so what do I mean by specialized? They're basically things that are hard to fit into this example column. And so I thought just to illustrate that point, I would highlight one example from the recent literature. So some of you, if you were here maybe 2 years ago, you might have attended Pat Holland's lecture. And he's done a lot of wonderful inorganic chemistry across a range of different topics. And one cool report from his group demonstrated actually a T-shaped nickel-1 complex. And so this is sort of what I mean when I say something is specialized. So this takes advantage of this beta diketimidate ligand with this very bulky aryl group dip. Does anybody for a starburst know the structure of dip? Diisopropyl phenol. 2 and 6. So this is a common. There are a lot of ligands that are derived from this aniline. So Barry Sharpless has some interesting theories as to why isopropyl groups in terms of ligand design tend to be more prevalent than terbutyl groups, and essentially it amounts to the fact that isopropyl groups are a little bit more conformationally flexible, and terbutyl groups are really always in your face. And so anyway, I don't want to belabor this point, but there are examples of these geometries as well. They often require more specialized ligand environment, and interesting when you observe them in their own right. Okay, so moving down in terms of geometries with coordination number 4, the two possibilities here are either square planar or tetrahedral. And so you'll see many examples of both of these, but I've just highlighted a couple here. So rhodium chloride tris triphenylphosphine is an example of a classical square planar complex. And in terms of tetrahedral ones, probably one that many people in this audience have worked with, palladium tetracus triphenylphosphine, and another that also I'm sure many people have worked with, titanium tetrachloride. And so in terms of just simple VSEPR analysis, a tetrahedron, of course, is the most stable way to accommodate for electron pairs around a sphere on steric grounds. But in many cases, particularly, we'll come back to this point, but particularly D8 metals are almost always adopt the square planar configuration. And so the tension here is between electronic properties or electron valence and steric properties. Hopefully this will become more clear later. And then two more quick examples. So for coordination number 5, square 5-pyramidal. I have an example here of vanadium oxo species. And then coordination number 6, this is sort of the archetypal coordination complex, octahedron. Many, many examples. We saw the Werner complexes earlier, molybdenum hexacarbonyl, iron aqua species. And so the three that I think are most common and probably most relevant in terms of today's discussion in this class, I've highlighted with a star. So I think if you understand these three in a fair amount of detail, then you'll be able to understand the others as they come up. And we'll go through each of these in a more detailed treatment later in today's class. So from this VSEPR theory, we can have a sense of what geometries might be possible given a particular coordination number. But there are many properties that are not directly derivable from this analysis. And two that people were aware of as early as the 1950s, 1960s, were the inability of this framework to explain properties like magnetism and color. So it's very obvious that many transition metals, we talked about ferrocene in the last class, it's obvious that ferrocene is colored, and this analysis cannot explain the origin of that phenomenon. And so this knowledge gap led to the development of an improved and more advanced theory, which is known as crystal field theory. So we'll spend most of the remainder of the class today talking about this. The early development of crystal field theory actually predates some of the origins of what we now think of as organometallic chemistry. So you recognize this predates the first report of ferrocene. So this really comes from sort of an inorganic perspective. And the goal here was to develop a framework that allows us to explain the breaking of degeneracies of electron orbital states to a static electric field. And so one of the key points, and I'll highlight this, because it's important as we talk about motivations for the development of ligand field theory is that in this framework, ligands are treated as point charges. And so the basic idea is that if you consider the ligands, which invariably have negative charge associated with them, and the metal, particularly as it gets to +1, +2, etc. oxidation state, you have partial negative charge on the ligand, partial positive charge on the metal, and these two partial charges lead to attraction. And as these ligands, which always coordinate with defined geometries, as these ligands approach the metal, the electrons from the ligand will repel the electrons in various d orbitals on the metal. And because these geometries are defined and the d orbital geometries are defined, a given ligand set will repel certain d orbitals more than others. And so the closer a d orbital is to an incoming ligand, the higher energy that d orbital becomes. So if we take an extreme example and think about the dz squared orbital, as we're adopting an octahedral coordination environment, you see that this orbital will become higher energy. Also, the dx squared minus y squared orbital will become higher energy because it's directly along the axes that the ligands are coordinating. And so then that gets reflected in this orbital splitting. And so the amount of splitting is affected by many factors: the metal, the oxidation state, the ligand identity, as well as the geometry. And so I think that this is perhaps most clearly illustrated by just talking through a few representative examples. And so we'll go through a few, we'll work through some problems today, and hopefully this will become clear. So if we consider the 5 d orbitals on the metal, they're drawn here for clarity. And thankfully, Phil wasn't teaching today, so I was able to sneak in and draw these d orbitals without the pressure of eyes watching. So for comparison, let's first consider what a spherical ligand field, what is just a spherical, non-directional electric field would look like. All of these orbitals would become, they're all degenerate here. They would all become degenerate in a spherical ligand field. And they would all become higher energy because it's negative charge repelling negative charge of the ligand field. And now what happens in an so this is spherical, what happens in an octahedral field? As I mentioned, the dz squared orbital and the dx squared minus y squared orbital, they directly clash these point charges as they're being brought from infinity towards the metal center. So in an octahedral complex, there are 2 point charges coming here, and there are 4 coming here. And so these become higher energy. So that you see this is the dz squared and dx squared minus y squared. Because of molecular symmetry, we call these Eg. I don't have, it's outside of the scope in this class to talk in detail about molecular symmetry, but suffice just remember that in an octahedral ligand field, that the dz squared and the dx squared minus y squared become Eg symmetry. And because this effect is somewhat pronounced, you see that actually most of the energy increase compared to energy decrease, which I'll talk, most of the energy increase is captured in this term. And then if you consider these same octahedral point charges approaching the metal, then in comparison, the dxy, dyz, and dxe orbitals are less affected because the lobes of these orbitals point away from the incoming point charges. So they're all affected, but they're less affected than in these two cases. So these are actually low energy compared to these orbitals. And so this is this orbital splitting. And so this is expressed as 0.4 times the overall splitting. And so you'll see this delta term as a descriptor for orbital splitting in crystal field theory analysis. And then different geometries have different partitioning of the ligand field splitting energy. And so these three orbitals also get a new symmetry name, and that's P2G. Again, this is just something that you should remember. And so one of the things that becomes very powerful is that different d orbital counts have specific geometries associated with them. So you can, as you're doing your analysis and thinking, okay, this is a d6, then immediately in your mind you can start thinking about octahedral complex. So octahedral coordination geometry is common for d0, d3, d5, and especially d6. I think this is one of these things that should just be drilled into your mind. D6, octahedral. And remember that D6, this connects back to a lot of stuff we've already seen. For example, cobalt +3 and the Werner complexes is an example of a D6 octahedral metal. And there are others that you'll commonly encounter. Okay, I went through that quickly. Are there any questions on that? We can work through two more examples, and hopefully that will become even more clear. And I've seen the light in terms of using a wet cloth to clean the blackboard instead of the eraser. So let's consider the other two scarred geometries. So first we'll consider tetrahedral. In the interest of time, I won't draw this. I'll just draw a simplified version of this orbital diagram rather than the full treatment like I did with the octahedral. Okay, so if we return to thinking about these orbitals and now these d orbitals, and now consider a tetrahedral ligand field. Could you adjust the camera back over here? Now you will appreciate that essentially it's the exact opposite situation to the octahedral. So in the octahedral ligand field where you have point charges approaching the metal directly along the x, y, and z orbitals, then of course the dz squared and the dx squared minus y squared become high energy. Now in a tetrahedral ligand field, the point charges are coming and they miss both of these orbitals and they interact in a much more pronounced way with these three. And so in terms of how the symmetry is broken, now these, how the degeneracy is broken, the other three d orbitals, dxy, dxe, and dyz become higher in energy, and the dz squared and dxy squared are lower in energy. And another important factor here is because there is not like this head-on collision like there is in the octahedral case, the magnitude of the splitting energy is smaller than in the octahedral case. So you see it's only 4/9 the energy of the octahedral splitting. And this has really important consequences because that means that the energy I'll write this out and then I'll read it so everyone can understand what I mean. So as we are filling these energies, so let's just consider an arbitrary example where we're putting electrons here. And I think you'd recognize that we fill these two first. We'll come back to this in just a minute. But then you have a choice. You can either put the next electron here or here. And which of these you do depends directly on what the splitting energy is and whether the splitting energy is larger than the energy cost of putting two electrons in the same orbital. And so this has very important ramifications in terms of property that we'll come back to, which is whether the complex is high spin or low spin, essentially how many unpaired electrons it has in its ground state. And of course, that has direct relevance for properties like magnetism. So let's consider one more geometry. Which is square planar. And then on one of your handouts, you'll see that there are similar crystal field splitting diagrams for the other common geometries. It used to be in vogue to ask, like on a homework, like in my time as undergraduate or grad student, you'd ask on a homework, draw out the crystal field splitting pattern for a square pyramidal complex or something like that, or a trigonal bipyramidal complex, but because you couldn't find that information easily on the internet. But now you just search that and you'd have it in 15 seconds, so it's no longer a good exam problem. Or no longer a good homework problem, at least. For me personally, I find these which orbital goes where to be a little hard to predict a priori. I don't know if I'm the only one who feels that way. I think it's fine to rationalize it, but if I had to predict which of these would go where and by how much, I think that would be a little hard. Or if found it a little hard. So so now let's consider the case of square planar. It will immediately be evident that the d x squared minus y squared, where all of the lobes are pointing directly towards these point charges, that's going to be the highest energy. The next will be the dxy, because you're still getting repulsion, even though these are not directly on the lobes. And then the dz squared is the next, because you have that, remember, that little donut of electron density, and then these two essentially miss the point charges as they're coming in. And so the relevant splitting energy is defined as that one. Yep. And square planar and this is something that everybody should just commit to memory. Square planar is very common for D8 metals. So in this department where people are often working with palladium-2 as pre-catalyst, intermediate, palladium-2 is square planar, palladium-2 is D8 metal.
The
Yes?
energy level, should it be dxc and dyz?
What did I write? Let's see.
dxi twice.
Should be dxy.
The top one's right.
Yeah.
Oh,
The bottom one.
thank you.
Just wrote dxy twice.
And so you're saying this should be dxz.
Yes.
Okay, thank you. You get a starburst for correcting. So one of the, of course, one of the central points of crystal field theory analysis, just to recapitulate something I said earlier, is that it's not a depiction of bonding, right? At no point are we considering bonding. The ligands are just treated as point charges, and so. So from that framework, it's hard to build up from first principle which ligands are going to interact with metals more strongly than others. And so what folks rely on, what turn to is what's called the spectrochemical series. And there's a handout that summarizes this in more detail. And so this is just an empirically derived trend measured spectroscopically where you're able to read out empirically what this splitting energy is, and then from that deduce which ligands have strong impact in splitting and which have weak impact. And so that's useful for predicting things like what's high spin, what's low spin, but it is not useful in terms of elucidating in terms of bonding why this is the case, or to offer predictions about what ligand is going to be more or less strongly bonding. And so this is an incomplete, intentionally incomplete spectrochemical series. More detailed one you can find in your handout. But ligands like iodide, bromide, chloride, fluoride, alkoxides, these tend to be low field ligands, whereas some of the softer, well, this is iodine is also soft, but some of these more strongly bonding ligands, we'll talk about what that means later, but like phosphines, CO, hydrides, alkyls, these tend to be high field ligands. And so we can make predictions about things like spin state versus based on the spectrochemical series. Oh, actually, while I jot down these notes, let's jump to, I think we've covered everything we need for problem of the day, number 1. So let's jump into that. So let me read that out loud. Cyclometallated palladium species A rapidly undergoes oxidative addition with organohalides, the alkyl or aryl, to give a new complex B. And so your first task is for both complexes to provide the coordination number, d electron count, geometry, metal oxidation state, and total electron count. So that's essentially the same kind of treatment that we were doing last class with the addition of geometry. Part B is to provide the d orbital diagrams that are predicted based on crystal field theory. And then part C, which builds on part B, is to predict which d orbital is going to be involved in this oxidative addition step. So we'll cover oxidative addition in more detail in the next 2 classes, but you don't actually need to understand that in much depth to answer this question. Does anyone still need either of these 2 panels? Feel free, as always, to discuss with your neighbor. People are still working on minor parts, but let's ask someone to take a stab at part A of this problem. Kai, do you want to go help us with defining these values for complex A?
Okay. The coordination number for the complex is 4.
Let me just draw this quickly. Okay, keep going.
And the electron configuration is D8.
4. D8. Okay.
And I think it's a square planar.
Okay.
And the oxidation state is +2. The total electron count is 16.
Okay. Anybody get anything different from that? So Kai worked out that this is a D8 complex, and we just learned that D8 complexes are normally square planar. Very good. And what about B? Dongman.
So the coordination number is 6.
Okay. I'm going to catch up to you one sec. I'm pretty fast at drawing these cyclopallidated complexes over a few years of practice. Okay, coordination number is 6.
So D6 complex.
D6. Okay.
Counters oxidation.
Okay.
Oxidation state +4. And the electron count is 8.
Total electron count. Okay. Anybody get anything different? Okay, so Dongman nicely worked out that this is D6. We just learned that D6 complexes tend to be octahedral. I guess for 6 things of 6 coordination number, they're essentially always octahedral. Okay, and now d orbital diagrams. I'm not sure what the best way to tell me what your answer is for this, but without drawing it. So Vincent, how many, let's first consider A. So how many orbitals are there in the lowest energy?
2.
2, okay. And then what?
Then 1 at the next.
1,
And 1. And 1.
Okay. So this is essentially this same diagram from square planar. That's not so surprising. But now let's do something we didn't do earlier, which is let's fill in the electrons here. So this is D8. So tell me where to put electrons.
I think you'll put 4 in the lowest energy.
Okay.
And then 2 in the next.
Okay.
2 in the next as well.
Okay. And so now this will become relevant. This will become relevant for part C. Let's make sure that we define which orbitals are which. Okay, now I need to make sure I do this right. Okay, very good, Vincent. And Alex from Florida, do you want to take a stab at this one? Do you have the microphone? Okay, hey. So how many orbitals in the
3
ground state?
Well,
3. Okay.
those are this P2G set,
Okay.
Z squared and squared plus 1 squared on top.
Okay. Oh, Alex, we can't throw you a Starburst over the internet. But last year,
That's fine.
I bought
I'll imagine you
on
did.
some. I bought Hans some Starburst to give to Emma, so I'll do the same this year. So you can have a whole bag of Starburst.
Great.
Okay, and Alex, let's fill these in as well. So this is D6.
Probably all on the bottom.
All on the bottom, okay? And so what are the considerations for filling up the bottom versus potentially filling up this top?
Might be favorable to have two unpaired electrons in the top.
Yeah, so you could potentially, for those last two electrons, they could potentially go here if this was small. But this is octahedral. We have some strong field ligands, so this is expected to be high, so we fill in these first. Okay, very good.
Can you predict that a priori, or do you have to do something to figure that out?
You can predict it a priori. The next section, we'll talk about that. So you see I started to fill this in, high spin versus low spin. So if after that part it's still confusing, then be sure to ask a follow-up question. Okay, thank you very much, Alex. And then Zhang, how about the last one, part C?
I imagine that the ligand would interact with the lumo of the d orbitals, so I guess it would have to be dx squared minus d minus 1 squared.
Well, remember that, okay, let's first just start out by saying for an oxidative addition step, remember that ligands are going to be flowing off the metal. So you need an occupied d orbital here, and then you need to be populating an unoccupied orbital. Does that make sense? So in general, on the metal, you're going to be looking for what are occupied orbitals that are high energy.
I see. In that case, it's dxy.
Okay, so the two, yeah, so let's just star both of these as being high energy. And now the question tries to set this up a little bit. There are two factors. There's the steric consideration and the stereoelectronic consideration. So remember that the dxy, so the dx squared minus y squared is directly here. The dxy is like this orbital that's here. The dz squared is going to be this orbital. Okay, so we know from this analysis that the dxy is higher energy, so this is the HOMO. And then let me ask a follow-up question. Based on steric grounds, would you say it's accessible?
Probably not.
It's less accessible,
Yeah.
certainly, right? Whereas you have this nice filled dz squared orbital that's right in the middle of free space, essentially. Okay, so if you had to pick one, which would you pick?
Well, based on our analyses, I would say dz squared.
Okay. I think that's reasonable. Anybody get anything different or have questions about this?
How
Yeah,
do you infer that by experiment? I think there might be some intermediate direct go to the 6 ligand species, but maybe some 5 or 5.
That's right, yeah. So we'll get to this in the oxidative addition section. For this type of oxidative addition, depending on what the electrophile is, there could be different paths by which the reaction is happening. So if it's an alkyl iodide, for example, then you can go through a 5-coordinate intermediate. How would you test this? Do you have any idea? Or how to test? Your question is how to test what the mechanism is, or how to test what orbital is involved in
I think
oxidation?
it's both.
Both.
They are related, right? So how to test is the disease will happen to the oxidation and
Yeah, so I think that's a really good question. And I think we'll talk about some of the mechanistic aspects of the oxidative addition step later. So after that, if this part is still unclear or you still want to discuss further, let's discuss it again. Tyler?
Just to add, also you'll notice when you go from square planar to octahedral, the DC squared has higher energy in its own field. So it's most likely what's getting oxidized. Whereas the EXY is lower.
Okay, just in case anybody didn't hear that, since Tyler was not mic'd up, he's noting that after oxidative addition, the DZ squared orbital is actually of EG symmetry and is unfilled. And so the argument here is that that is more likely to be involved in the electron transfer step, which is required for oxidative addition. Did I restate your...
Is it true that for some systems with square planar geometry, the dz squared becomes actually above the dxy?
Do you have any examples?
Depending, well, I cannot recall specific examples, but I think I've seen, depending on the ligand, the metal, sometimes that can be the case.
I don't want to say that's never the case, but I think it's not commonly the case. So maybe if you find some examples, we can discuss those offline. Yeah. Really good question. Yeah.
What are the values for delta oct typically like in kPounds? Do you have an idea? Like how high is high energy?
I don't know the answer to that, and so I can look that up and
So here they are
provide
given
more information.
inverse centimeters, so high field would be about 20,000 inverse centimeters, and kpound that's probably about,
Oh, I can
so it's only come out with crystal field there. So from about 20,000 inverse centimeters, it's usually low spin 6.5.
So yeah, these values can be experimentally determined spectroscopically, and then so from, for example, the wavelength of the light energy that's required to excite an electron, you can measure out what the energy gap is and determine it. It sounds like these values are available on the handout and they're quoted in
Yeah, they are
wavelength or wave
half of
number.
the table. Yeah.
But is it over? Does that say delta over delta oct? I can't read what the...
I think it says delta in wave numbers, so delta in centimeters to the power of -1.
Definitely a division statement.
No, it's the units.
Okay, very good, everyone. Let's move into discussion of what Alex nicely set us up for, which is a discussion of the factors and how to predict high spin versus low spin, or at least how to think about that. How to predict can be harder. And so to make this point, let's consider, I think this is clearest by going through an example. So let's consider iron 3, which is D what? Anyone want to jump in? D5. I heard a lot of people, so just throw starburst everywhere. D5. Okay, and D5 would typically be what geometry? It's also obvious from this, octahedral. scenarios where either the splitting is large, this is a weak field ligand, or the splitting is small, this is a strong field ligand. And so now we've got 5d electrons to put in here. Energy gap here is large, energy gap here is small. So let's go through this. So we first populate these 3, and then we have a choice. Are we going to go here or here? Because this is large now, populate the T2G, doubly populate the T2Gs. And in the weak field case, then it's lower energy to populate the higher. So this is essentially a competition between two fundamental properties, or fundamental principles. So one is this Aufbau principle. Which says, in essence, this is a simplification, but in essence, that lower energy orbitals should always be completely filled first. And the other computing principle is Hund's rule. Which says that if two orbitals have equal energy, so sometimes these are in conflict. Aufbau principle says that we should always fill low energy orbitals before we move up. Hund's rule says that for a given degeneracy, we should fill every orbital. And so when these become very similar in energy, then Hund's rule can actually dominate. Okay, so this will take us to problem of the day number 2. There are 3 coordination complexes, and you're asked to predict whether they be high spin or low spin. And so you're going to want to take into account what we just learned about, what kinds of ligands based on the spectrochemical series are expected to be strong field versus weak field. So take a minute to think about that. Draw what these examples are.
Sorry.
It's like high.
Okay. So let's give your answer and explain your reasoning. And then I will draw the orbital diagrams as needed. Okay, Hansol. No, letter A. Cobalt. This cobalt aqua complex. Low spin. Okay. Can you explain your reasoning?
It's hard to say because the water ligand is kind of in the object, but it's like C stiffly.
Sorry, what was the last thing you said?
It seems that like C stiffly high speed.
Okay.
So for this A could be.
Okay. So Hansol's pointing out that there are two more extreme cases, and this is maybe a more intermediate case. But just quickly walk me through your like d orbital analysis, geometry analysis. So cobalt 3+ is what?
It's D6.
D6. So that's going to be what geometry? Octahedral.
Yeah, so all
Okay.
6 electrons will and the low 3 ohms.
So then the question is just, is this high field or low field? And you're saying it's high enough field? So you're saying it's this low spin.
I thought most like D6 metals were like this configuration because I mean you get stabilization by having everything paired instead of just having like a bunch of unpaired electrons. Like are there examples of D6 metals that are not this configuration?
D6 metals that are not octahedral or what?
No, that aren't that don't have a select subpair. That aren't the high.
Yes.
Like what?
We just saw. Yeah, we just saw this example.
Wait, but that's a D5. For the problem we're talking about, letter C is an example.
Oh.
I think oxidation state maps are terrible because I remember most of the +3 complexes are those people.
Okay.
Because
So
it
yeah,
comes
the question is basically like this, like this. And so in this case, it's good discussion. I think you're thinking about things in the right way, and in this case, it's the high spin situation. So aqua ligands, even though on the board I drew them as being kind of in the middle, I think if you look at the whole spectrochemical series, they're actually on the weaker end. So when we cut to back bonding, strong field ligands tend to be ones that can engage in back bonding. So let's just say this aqua is a weak field ligand. This is small. And in that case, Hund's rule predominates.
So where would you say the cutoff in the spectrochemical series is then, between weak and strong? I mean, obviously you can include any
random ligands one, right? But generally, like, is there a way we should think about it?
Well, I think when you get to the boundary, you're going to want to do the measurement, right? And so I think, in general, as I've drawn it here, in general, all of these are weak field.
So, like, anything without back boundary?
Yeah, more or less. Okay, good. That was a good discussion, and I think that will make B and C probably quicker. Jess, B, and Stephen, C. B is high spin. Can you very quickly walk us through your reasoning?
Because the electron ligand is a
Okay. Would that make it high spin or low spin? Is this a strong field or a weak field ligand? Strong field ligand, so more likely to be high spin or low spin. When you have stronger partitioning, then you're more likely to populate low energy orbitals, so that makes it more likely to be low spin. Okay? And what's the geometry of this very quickly? 4-coordinate. Nickel 0. Square planar. Okay.
Nickel 2.
Nickel 2, sorry. I just misspoke. Yep. And then last one. Stephen.
So it's a D6, which is octahedral in this case. You have, low splitting fluorine, so it would be high spin.
Okay. So that's essentially the same situation. Good, and we'll have more chances to practice those and think about those and think about exceptions to those general rules as we go through the homework. So in the remaining 15 or so minutes, I'm just going to quickly go through a couple more points. Phenomenon called Jahn-Teller distortion, Jahn-Teller effect, which is actually a general phenomenon that refers to spontaneous symmetry breaking in many different contexts, but in terms of coordination chemistry, what it is referring to is a scenario where let's consider a D7 low spin. Octahedral. This spontaneous symmetry breaking happens whenever you have unequally occupied degenerate orbitals. Sometimes this happens, but it's the effect is not big enough for you to observe. And so here is a degenerate set of orbitals. They're unevenly occupied. And so what that means is that these are going to break symmetry to lie in a lower energy state. And so then the orbital splitting pattern will become a distorted octahedron. Where the you're basically moving these 2 point in crystal field theory analysis, you're moving these 2 point charges farther away. That weakens the repulsion with the dz squared, so that's going to become lower energy than it was before. So those two split. And in terms of the structure, that will manifest itself by seeing elongation of those two. Okay. So now we're going to take the remaining time to introduce ligand field theory, and I think we won't quite get through everything, so we'll take the first 10 minutes of the next class to get through the last few points. But as I've said several times, crystal field theory says nothing about bonding. It's treating all the ligands like point charges. And this is fine for making predictions about what the d orbital energies look like, how to think about that, how to make predictions. But it doesn't say anything about bonding, and it really doesn't explain why different ligands have very different effects on properties like color, for example. So folks were aware that this was an incomplete picture. And so in the 1950s, it was an active topic to sort of develop a refined version of this that could integrate what was known at that time about bonding, particularly MO theory, with crystal field theory. So can you superimpose molecular orbital theory onto crystal field theory and get a system that has more predictive value? And so this would ideally explain the difference between why fluoride as ligand and ethylene as ligand have sort of completely different properties in terms of their interactions with the metal. And so there are textbooks that treat this topic with extreme amount of detail. You'll note that the Hartwig textbook basically doesn't cover this. It's sort of outside the scope of what's included there. The Crabtree textbook covers this a little bit. And so I would say this will not be a primary focus of the course, but I want to give you a quick primer in ligand field theory because I think it's very helpful to have this as a background and to know how to think about back bonding, especially. So I'm going to draw now a very complicated orbital diagram, and then I'll unpack this with what remaining time we have left. So as we said, we have the 18-electron rule states that we can so again, I'm using these molecular symmetry descriptors. Details aren't super important here. So we said on the 18-electron rule, we have 5 d orbitals that are involved in bonding, as well as a higher energy, so 3d, in this case 4s and 4p. And remember that in terms of MO theory, these all have different symmetries. So we have these orbitals on the metal. Let's say this is a D1 metal. So the complex that we're going to be considering here is this titanium aqua complex. So this is D1. And so this is octahedral. So there are now 6 orbitals that are going to be involved in bonding in the ligand. And some of these are going to be symmetry matched to certain orbitals and some others. So the A1G pair with A1G orbitals here, the T1U pair with T1U orbitals, and the EG pair with EG orbitals. And so remember that these, the 3D orbitals can partition into either T2G, but you see there's no T2G symmetry here, or EG. So the orbitals that have EG symmetry are the dz squared and dx squared minus y squared. The orbitals that have lobes that lie directly along the axes are going to be the ones that can interact with the metals that are coming in directly along the axes. And then those of T2G symmetry, of which there are 3, become non-bonding. So let me quickly just kind of try to draw straight lines and show you what orbitals are going where. And these, well, one thing, now it's too late, but these ligand orbitals should be lower in energy. Can't do anything about this now, but these should be down here. Ligands lower than metal. Okay. I guess I can just quickly change this so it's clear. So one of the things that hopefully becomes evident is that this is a more advanced treatment because we're superimposing MO theory and crystal field theory. But in terms of the frontier orbitals, it collapses to the exact same picture that we see in crystal field theory, where now you have filled non-bonding d electrons, d orbitals, singly populated T2G symmetry, and non-bonding unfilled EG orbitals. Yeah.
Why are the ligand orbitals divided into 3 individual orbital sets? Like, what do those represent?
These are different symmetries.
Why are they different in symmetry when they're coming from the same thing? Like, are those just supposed to represent like the orbitals holding the lone pairs on water, or what are they?
All the molecular orbitals. What are the linear combinations of these? It's all six.
Right. It's the linear combination of all bonding and orbital lobes of 6 ligands.
I think the first step is to form group orbitals, maybe to look it up.
Right. Yeah, so these are group orbitals So this is sort of an MO treatment of 6 ligands that are all going to be engaged in bonding and antibonding. So maybe we can chat more about that. After class. Okay, and the key point here is that the dz squared and dxy squared engage in bonding and antibonding here and here, and the other 3 d orbitals are engaged in non-bonding interactions. So when they have electrons, they can engage in back bonding to the ligand. If they have open sites, they can accept a p orbital, a pi bonding interaction from the ligand. And so we'll talk about that at the beginning of next class. And I think the next 2 problems of the day will be we'll cover right at the beginning of the next class. And I want to leave you with the chemist of the day. Anybody want to make a guess? Hazard a guess? Tanner guessed Crocodile Dundee. It's close. Some Australian. This is Jim Coleman. In his younger years. Still alive now, emeritus professor. Started his career at UNC Chapel Hill. And then moved to Stanford. You'll perhaps recognize him as a postdoc supervisor of Barry Sharpless and Bob Grubbs. And among his many contributions, one of the things that he's credited with that is relevant to today's lecture and Wednesday's lecture is formulating fundamental principles of structure and bonding, as well as reactivity, across the transition metals. And this is one of his seminal reviews that I'd recommend reading. So prior to this treatment, people would analyze a group of transition metals, and they'd publish a review on that, or they'd publish a textbook on that, or a certain class of ligands, like all complexes with only carbonyl ligands. They'd write a textbook on that. But of course, this is a somewhat myopic view of bonding and reactivity, and so Coleman's one of his many contributions, as I said, is to really put together a broader picture and recognize that metals with a certain d orbital count react similarly, and there's actually predictable patterns here. Good. Okay, we are dismissed. I'll stay after if there are any questions.